Take a look at the heavy distortion radiating off these flames. If you stand near a bonfire on a freezing night, your face will feel intensely warm, but the winter air sitting directly between you and the fire remains completely cold. We experience a similar paradox every summer. If you stand in direct sunlight wearing a black shirt, your back heats up rapidly. A friend right next to you in a white shirt, dealing with the exact same air temperature and sunlight, stays significantly cooler. To understand why, we have to look at the strict rules of physics. Heat transfer through conduction requires direct physical contact between vibrating particles, like a metal spoon heating up in a hot bowl of soup. Convection requires the upward movement of liquids or gases, like hot air rising from a heater. Neither of those mechanisms explains the horizontal warmth hitting your face from the bonfire. And more importantly, conduction and convection require physical matter to work. They cannot explain how the sun's thermal energy travels across 150 million kilometers of absolute empty vacuum to warm the Earth. A third, invisible mechanism must be at work, one capable of transferring massive amounts of heat without relying on any physical substance at all. This shows how the sun's energy reaches us: radiation. It transfers heat through electromagnetic infrared waves, requiring zero physical medium. Shifting to thermal heat signatures reveals a universal law. Absolutely all objects emit thermal radiation. Hotter objects emit more intense radiation. An object's temperature isn't the only factor at play. The physical texture and color of a surface dictate how it interacts with these waves. Darker, rougher surfaces act like sponges. They are highly efficient at absorbing incoming radiation and emitting high levels of radiant heat. Conversely, lighter, smoother surfaces reflect radiant heat away rather than absorbing it. That is the reason the black shirt absorbs the sun's rays and bakes your skin, while the white shirt deflects them. Radiation operates as the primary thermodynamic engine of our planet Earth, governing how solar energy enters the atmosphere, cycles through the terrain, and eventually vents back into the void of space. Because of that continuous solar radiation, the Earth's oceans and atmosphere function as a giant thermal engine. The global water cycle serves as a massive planetary heat transfer system. In this cross-section, incoming solar waves strike the water. As the liquid absorbs that radiant heat, its molecular kinetic energy, the physical energy of motion, increases. The water molecules vibrate faster and faster until they break free and escape as vapor. This is evaporation. Following that vapor upward, convection takes over. The warm, moist gas rises into the cooler layers of the atmosphere. As it travels, it loses heat to the surrounding air, the molecules slow down, and the vapor clusters into clouds in a process known as condensation. Once those clusters reach critical mass, they become too heavy for the air currents to support. The system mechanically releases this accumulated moisture back down to the Earth's surface as precipitation. By pulling water up through evaporation and dropping it back down miles away, the water cycle continuously redistributes the sun's radiant heat energy across the globe, maintaining a livable climate. When that precipitation hits the ground, it undergoes infiltration. The water slowly seeps downward through millions of tiny, porous pathways in the soil, sand, and rock layers. Eventually, it settles into aquifers. Aquifers are deep, saturated underground rock layers that act as massive, slow-moving reservoirs for our planet's freshwater. By tracking how local temperatures drop and mapping these natural water cycles, humans have learned to engineer survival solutions in both bone-dry and freezing climates. Look at this towering structure in Ladakh. This is an ice stupa, an artificial glacier. Engineers create it by spraying and freezing pipe water in the frigid winter air. It stores the frozen moisture in a cone shape specifically designed to minimize surface area, ensuring it melts very slowly through the spring to provide drinking water. Mastering the principles of heat transfer and understanding how water changes states is exactly what allows populations to sustainably manage their resources in some of the harshest regions on Earth. Despite relying on these physics every day, our daily instincts about hot and cold are often scientifically backwards. Our physical senses routinely lie to us about what is actually happening. Heat consists of the kinetic energy of particles vibrating violently in place, transferring energy to its neighbors without any material changing location. Another instinct tells us that thermal radiation needs air to travel. but watch as the particles fade out. Pure infrared waves travel perfectly through a complete vacuum. They even pass effortlessly through transparent solids, penetrating a pane of glass to warm whatever is on the other side. Finally, we tend to believe that insulation permanently stops heat. Insulators like wood or plastic possess a low thermal conductivity, meaning they have a poor ability to allow heat to pass through them. They strictly delay the transfer of energy. They cannot stop it entirely. Discarding these sensory illusions and understanding the true mechanics of thermal energy is the mandatory first step for engineers trying to control our modern environments. To see all three modes of heat transfer defeated at once, you just need to look at an everyday object, the thermos flask. In this cross-section of a thermos, you can see the brilliant architecture at work. An empty vacuum layer separates the inside from the outside, entirely neutralizing both conduction and convection, since there are no particles to vibrate or circulate. Meanwhile, a mirrored inner wall reflects the liquid's own infrared radiation right back into the coffee. But the laws of thermodynamics are absolute. Even within this highly optimized design, thermal equilibrium, the point where temperatures finally balance out and heat stops flowing, will eventually be reached. Your coffee will still cool down. It just takes much longer. Understanding heat as invisible, transferring energy empowers us to build smarter technologies, stay safe in extreme climates, and protect the thermal water cycle that sustains our planet.